Okay, hey, this is chapter 14, groundwater and erosion. I get so excited when I talk about groundwater because it's our world's most precious resource. When we think about how important water is to us, um, we can go quite some time without food, but when it comes to water, uh, we can only go a couple of days before we start to get dehydrated, and it causes a problem. Now, erosion will play a big factor in groundwater and how we get it. And so bringing them two together is very important, not just for our farming communities, but everybody. So what we're going to talk today about is 14.1, water beneath the surface. And our objectives are simple. We're going to distinguish between porosity and permeability. We're going to identify the two moisture zones below our surface and to discuss how they relate to each other. Then we're going to relate the contour of the water table to the contour of our land, and then describe how groundwater can be polluted. Moreover, how it can be prevented. So if we take a look at this map or this diagram, this is just like us with the exception of the mountains, right? So we have a river and we have towns and we have agriculture and farming, and we have communities that rely on this little thing right here, which is a well, or like some of us, we get our water from the river, and the river is then pumped to a storage facility, cleaned up, and then pumped up into our water tower for delivery to our homes. So what this is picturing here is what's beneath the surface. We call that an aquifer. And the aquifer is very much like a storage area for our water. And so what happens is our water that falls to the ground, it eventually percolates to the ground and it goes somewhere. We call that our aquifer. Now, if you look at this image, this is really about the water cycle, right? So we have precipitation that falls to the ground. That water either goes into a river or a lake or a creek, or it goes into our ground. When it goes into our ground, you're going to find this interesting. It's called, wait for it, groundwater. Right. And so groundwater is the area where water is flowing through our rock. And depending on how many holes are in the rock, it'll determine how well it flows through the rock. Now, with that being said, this is constantly going in a circle, right? So it evaporates either from the ground or from an area like a lake or a river, and it then goes back up to the sky. And so it's constantly moving back and forth. If you look at this diagram right here, and I'll move my picture here. If you look at this diagram right here, essentially what we have is our area, which is right here, which is primarily deep bedrock. And we are mining deep bedrock limestone in our quarries around here, and that's where they basically get rock for our road or making concrete or anything like that. But you'll also notice that not too far from us, we have things like sand and gravel and areas where water does infiltrate a lot easier. So these are the principal aquifers of Illinois. I'm going to drill in here. We'll go to our aquifer a little bit closer. So if we look at Livingston County, we see that over on the east side of our county and along our river, we have a lot of sand and gravel aquifers. And those sand and gravel aquifers, water flows pretty easy through it. But we also have areas where we have this bedrock. And depending on where you're at, there are some homes in our community that's very difficult to get water to flow if they have a well, and they have different types of wells. They have bored wells, which is basically a straw into the ground, if you will, very deep. And then they use that to pump water up out of the bedrock. Or you have a bored well, which is in my case at my house, where it's a big round hole, 24 inches in diameter into the ground, not very deep, but because we're in this sand and gravel area, water flows in there pretty well. And so you can see that depending on where we're at is the type of ground or bedrock that we have, or aquifer conditions. And it's interesting. I'm gonna go one below us here into a real unique aquifer, which is the Muhammad Aquifer. Now, Muhammad Aquifer is that aquifer right below that I just showed you. This is an aquifer that is actually contained in itself. It doesn't interact with other aquifers, and it's kind of unique, pretty well known globally. And so there's been a lot of discussion about how to protect this particular aquifer due to the fact that it doesn't interact with other aquifers because it's cut off with the bedrock. It doesn't flow through here. So when we talk about aquifers, the first thing that we talk about is how many spaces are in the rock. We call that porosity. And so if I were to take a sponge and dip it into a big sink and pull it up, water would go right through the sponge, and depending on how many holes and how well connected those holes were, would determine its porosity. How well does it flow? And this porosity, if it's one solid piece of rock, like granite or something like that, it'll have no porosity. It won't flow at all. But the more spaces you have in there, the better it can flow. And our rock here, being that it's limestone, depending on how many cracks are in the rock, we call those fissures, will determine how well it flows. With regards to our areas of sand and gravel, well, it's like putting a bunch of sand in a bucket and then filling it full of water and drilling holes in the bucket. It flows pretty good. When we talk about sand and gravel and rock and things like that, sorting of the rock, in other words, like you'll put a couple marbles over here, a couple cards over here, a couple rocks, sorting things out, right? Well, it's the same thing with rock in the sense that rock that is well sorted, in other words, all of the rock is about the same size. If all of the rocks are about the same size, you'll have what we call high porosity. In other words, there's spaces in between the rocks. And I'll show you a diagram here in a minute, kind of give you a better look at it. But if we have rocks and sand and particles of all different sizes, it packs in there and all of those spaces gets filled. And so it doesn't have very good porosity. In other words, it has low porosity. So high porosity, big, all rocks about the same size, and you have these areas in between where water can fill in. And so if we look at this diagram here, you have well sorted material, we'll call it sand. It's got ridges on the side, and notice we have all these open spaces. But if we have poorly sorted sand and we were to compress this here, basically what would happen is it would pack tight and nothing would be able to flow. In our particular area, we don't have granite, but we have area that have cracks in our limestone. And when we look at limestone, we think about things like caverns and things like that. And that doesn't go into play for us, more of a southern Illinois, Kentucky, Missouri, Tennessee. But if we look at our limestone, more a little bit like this granite, we have cracks in there. And when we drill a hole down to do a well, if we intersect one of these fissures or fractures in the rock, then we're able to get water, and water will flow through there. And so just a real good diagram here. Permeability. So if it's porous, we have big spaces, and permeability means how well does it flow? And so if it's flowing just like you've turned on the faucet, that's high permeability. Low permeability, something like a clay that's been packed. Some ponds are sitting by themselves and they hold water because they have a clay barrier that water can't flow through. It's low permeability or impermeable, right? If this was sand, the water would just go through. So when it rains or we have precipitation, the water hits the ground and the water's got to go somewhere. So it could go into the river or it could go into the lake or a creek or something like that, or it goes into our ground. And so as it goes through our ground, the first area that is going through the ground is called the zone of saturation. And zone of saturation is that area where all of the pores are filled. Now that's at the bottom. And so imagine you've poured water into a cup and the level of the water is full. That would be the zone of saturation. The very top edge of that water would be what we call the water table. And our water table actually for our river is exactly the top of the river. That's where the water level is under the ground. So if you draw a line all the way back away from the river, that's the height of our water table and the top of our zone of saturation. Now, when that precipitation or rain comes down, it melts. As it's going through the ground, the dirt, the stuff on top, we call that the zone of aeration. And the zone of aeration is broken up into three main parts. You have the soil water. And so this is the area where all of the soil is surrounded by a thin film of water as it comes through. You have the middle region, which is basically that water has not moved away from there. So this is an area where it's dry until it rains. And as it rains or it snows and it melts, that water will travel through this area, get the dirt wet, and then travel on down to the soil water. And then you have the capillary fringe, where this is the area where the zone of saturation. So it's like if I put a piece of paper towel on the edge of a spill, that water will travel into that paper towel. And this is happening in our soil as well. And so the moisture is basically through capillary action wicking up into the soil. Now, the capillary fringe is above the water table. So in other words, that water is wicking up through capillary action up into this area. And again, I use the reference of a paper towel soaking up water. That paper towel is drawing the water up off the table. So if we look at our picture here, we can see our soil moisture, which is damp from the surface. And then we go into that middle belt that's dry, this zone of aeration. And it stays dry until we have rain or snow or something that melts. And it goes through the zone of aeration as a liquid until it gets to, by gravity, of course, the water table and the zone of saturation. Now, again, the capillary fringe is just above the water table because what's happening is that water is wicking up into that soil next to the water table. So how does groundwater move? Well, if we have a lot of water coming in other words, we have a precipitation event or a rain or snow or whatever, water's going in. And so it's creating pressure to where it wants to settle from higher elevation to lower elevation. In other words, it spreads out. And so we see pressure that way. But if the rock is more permeable, then our water will flow faster through the ground. And so depending on how permeable it is, will determine how fast it moves, or the velocity of groundwater. So the higher the gradient of the water table, the higher the velocity of the water. So it moves faster. Now, topography is important. Topography, the lay of the land, ups and downs. And we know around here, we definitely have changing topography due to glaciation that took place here. And so it's not just flat like everybody says. And the water table will mimic, it'll mimic a couple of things. The rise and fall of this water depends on how much precipitation we had. And with the permeability, depending on how well it flows, will determine how much water we will have in our aquifer. Now, sometimes we have situations where we have what's called an impermeable rock layer. In other words, water can't move through it. And so it develops this little area that holds water, kind of like a pond underneath the ground. And it's called a perched water table. In other words, the water can't flow through it. And so if we look at this diagram here, we have a perched water table here, which means water can't flow through this area. And so it's holding water above our zone of saturation. It's holding water above our water table. And so this is what we refer to as a perched water table. Now, as I've said before, and we've talked about, water is a renewable resource, but it's definitely something that has to be understood and managed, because it is in limited supply until the water cycle refills it again. And so when we talk about our water table, if we pump too much water out of the water table, it could take a while for the water to come back. And so as a result of that, we can use more than can be replenished. And so we have to think about the conservation of our water. And some places in our county, people don't have much water. And the reason being for it is they don't have a well that produces for their house. And interestingly enough, if you take more water than, say, your neighbors, it's possible for you to run your neighbors dry because their well doesn't go deep enough. And so groundwater conservation is a big thing no matter where you are. So again, if we go back to what we were talking about today, our goals were distinguishing between porosity and permeability, identifying the moisture zones, relating to the contour of the land. Again, the contour of land, water table follows the contour of the land, and then describing how water can be polluted. It doesn't take much to pollute. And so as a result, we could really cause problems when it comes to our drinking water. This is 14.1. Can't say thank you enough for you guys being awesome. I appreciate all of you and what you do to make our community better, our school better, our world better. So thanks, and hope you have a great day.